I'm sharing my screen. Just before that, want to open the drawing. Okay. Okay, now let me know once you can see my screen. So is it visible now?
Yes, sir.
Okay. So today we are starting on ESR. So for that, I have chosen one practical example. Uh, this is a one drawing, general layout of the elevated storage reservoir. This is a section, this is a base slab, and this is a top slab, and this is an enlarged view of the tank, which is the container in which we are storing the liquid. Okay, so if you see, is it visible?
Yes, sir.
So this is a section. I'm starting from the top. So this is a top slab of the ESR. Obviously, this is a covered storage tank. And if you see, we have a roof slab of thickness 120 mm thick. And in addition to that, we have beams, roof beams. What is the size given? The 250 by 400 mm deep roof beams are there. So we have one central column over here, RCC column of 450 diameter. So it is a circular column having 450 diameter. Okay. And what is the clear height of the tank? The clear height of the tank is 5.7 meter from base slab up to the top of the roof slab. Okay. If we see the water elevation in the tank is a 5 meter, we have freeboard of 300 and after that 400 deep beam. Okay, clear?
Yes, sir.
And we have the cantilever peripheral walkway surrounding to the tank. The width of that walkway is 1.2 meter and the thickness of that cantilever slab is again 150 At base, we have certain floor beams and we assume that size of that floor beams are 250 by 750 Okay, and if I just go below that, now these are the some column structure or framing on which we have on top of that columns and beams we have placed our the entire storage container. Okay, so, so if we see the section, you can see this 1.1 3.18 by 3.18 something like that, 3.1 3.69 3.69, like we have created some bracing beams for the column. Okay, so if I now go to the plan at base slab at this level, can you follow my cursor?
Yes, sir.
At this level, if I want to take a plan view, so what will be that? So if I'm coming to this, so this is the peripheral 1.2 meter cantilever slab. Okay, this is a 200 thick circular wall, external wall of the circular tank, and we have some roof beams. Correct. So we have roof beams placed to support the base slab of the water tank, and we have some vertical columns. Can you see this from C1, C2, C3, C4, C5, C6 up to C9? Okay, so we have 9 numbers of columns on which our entire base slab and entire everything is going to be supported. Okay, so out of that, like from C1 to C9. Out of that, only C5, this central column is going up to the roof. Otherwise, except C5, all columns are going to stop at the base slab. Understand? Can you see this? C1, C2, C3, except the central one, C5. This is the C5. So except this, all columns are going to be stopped here. Okay, got it?
Yes, sir.
And now I'm going to roof slab. Suppose I want to take a plan at roof slab. So what will be there? So, okay, so this is the external 200 thick wall. Hmm. So this is C5. Column C5 is coming up to the bottom of the roof slab, or maybe at top of the roof slab. That's why we have shown only C5, and we have four beams. Okay, four beams on which one one quarter of each slab is going to be supported. Correct? क्योंकि span भी काफी बड़ा है ना. What is the diameter of the tank? Diameter. Where is the diameter? Yes, the radius, internal radius of the tank is 4.4. Means diameter of the internal diameter is 4.810, something like that. 8810. So almost 8.8 into 3.28 divided by, yes, 3.20. So almost 28 feet we have span. That's why it's impossible to support entire slab on only wall. Okay, so that's why we have added four columns, one column and four beams at a roof. Okay, so we can provide some support to this each quarter segment of the slab. Okay, got it? Any doubt regarding base slab, top slab? I am explaining the geometry, so we you can aware about the tank.
Sir, why is that cantilever is given, sir, that portion?
Which one? This
That
one?
cantilever, sir, that down, sir.
Yes. So we need some inspection, space for inspection. No?
Okay, sir.
आपने शोले देखा है कि नहीं?
देखा, sir.
हाँ, तो धर्मेंद्र यहाँ पे खड़ा था वो.
Okay.
ठीक है. So yes, so definitely we need some space for inspection. We need some ladder, so from that we can go on the top during some maintenance purpose. So that's why we need some operating platform. It's not mandatory. If you don't need, yeah, you can, but it's always good to provide some walkway so we can have some platform there. Okay. Okay, again I'm going to see this enlarged plan. So you can see this roof slab is 120 thick. In addition to that, we have 250 by 400 deep beam. This is the central column. Wall is 200 thick. Base slab 275 thick. Cantilever walkway 1.2 meter. Floor beams are there. And if I go to the section, so these are the isolated footings for each column. And we have provided some beams, cross beams, so it can be considered as a frame structure. On top of that, our container is going to be supported. Okay, and somewhere this is the ground level, maybe floor finish grade level. This will be a 0 means at this location we have some ground level here, and we are going 2.5 meter below ground. Okay, clear? Geometry clear? Okay, so now I will open one design report. So we did this design for ESR. So I can share this format with you also. So structural works design basics report for proposed circular elevated storage reservoir location Pune. So project description. What is the location of the structure Pune? Functional requirement, obviously water supply scheme for municipal corporation. Capacity 3 lakhs liter. Height of the structure above plinth. Okay, that is a 20.7 meter. Height of the RCC frame for structure. Height of the RCC frame structure for tank is somewhere around 15 meter. Depth of the circular ESR 5.7. If you go to the plan, this is the total 5 meter. 5.3 plus 4, that is a 5.7. Okay, depth of the circular ESR, that is a 5.7. Outer diameter of the circular tank is 9.21. Okay, so if we just make a summation, 4.405 into 2 plus 0.4, so 9.21. Correct. Outer diameter of the tank is 9.21. Planned dimension of structure, that is a 6.372 by 372. So if I just check dimension from this column center to this column center, this column center to this column center, it happens like a square. Okay, so that is a 6.372 by 6.372. Okay, construction type, I will just quickly go through that because this is very simple. Some basic information are given, so maybe you can also learn this very easily, understand very easily. Okay, so construction type, obviously RCC design. Grade of the concrete is a M30. We are using FE 500 mm steel. Design philosophy, so which codes that for to analyze and design for this ESR is used, that is IS 3370 part 1, part 2, IS 3370, IS 3370 2009 part 1 and 2, and we are also using the IS 456, that is a code for the concrete design. Okay, so these codes we are using for the our design purpose. Okay, so foundation, so we got this data from geotech engineer. If you don't know, maybe you can properly assume something with reference of code, because if you don't have anything in terms of geotechnical information, code gives us some basic guidance based on the soil strata, hard murum, soft murum, black cotton soil. So if there is such kind of things, so and if you don't know the geotech data, so maybe based on that you can appropriately assume something for your design. Okay. Okay, so in our interest is the safe bearing capacity of the strata. So we considered, based on the geotech report, we get 20 ton per meter square, that is our safe bearing capacity. Okay, and what is geotech mentioned? So we need to minimum excavation of 3 meter below ground level. So based on that we can get some hard strata, so we can get 20 ton per meter square safe bearing capacity. Okay, so angle of friction is 27 degree. So based on that, maybe you can calculate some Ka or Ko. Okay, so just for information, our main structural part will be something ahead of this.
So, but are there this one, no, sir? 2.5 was there, no, sir? That one, this one level depth.
Yes, that degree friction is 27 degree. Based on that, you can find out the Ka or Ko. 1 minus sine theta divided by 1 plus sine theta. Correct?
Okay, sir. Oh, sir. Okay.
Now, coming to the superstructure. Obviously, we have RCC slab and beam system. adapted for this structure. Lateral load resisting system will be consist of the combination of shear wall and moment resisting system. So what happened? So if I go back to the drawing, so this entire external wall of the tank, okay, so this tank wall will be act as a shear wall, correct? It's a uniformly cast single wall which is acting as a shear wall, and below this shear wall again supported on which this RCC frame, and this RCC frame, since because of this is RCC, it's obviously designed as a moment resisting frame, because obviously because of this connection there will be some moment, correct? So it's a combination of shear wall and moment resisting frame, okay. Standards, yes, we are using IS code. Design criteria, so now we have started calculating the dead load, okay. How to calculate, and what there are different types of load. So first load will be the obviously dead load, okay. So dead load shall be obviously the permanently there in accordance to IS 875 part 1, okay. So different types of dead loads, so now we are calculating the dead load. So basically what we are doing, so we are doing entire STRAD model. So self weight of the entire structure will be automatically taken care by the STAD. But in addition to that, we need to consider some additional dead loads. Which dead loads? So such as superimposed dead load for roof and base slab, unit weight of screed. Like these are some kind of the floor finish weight. Okay. So unit weight of the screed, that is our assumption. Unit weight of the screed is 24 mm, and what we are assuming, the thickness of that screed is 40 mm. What is the screed? Screed is a nothing but we, after casting of the base slab, we are providing some additional floor finish, or maybe you can call it as a waterproofing. So we need to consider that layer also, okay. And that thickness of that layer, okay, thickness of that layer is 40 mm. And where it is, so we have applied this layer on the base slab, top of the base slab, top of the roof slab, and even internal face of the walls also. So it can be act as a waterproofing element, okay. All good? Any question?
No, sir.
ओके, आज अविनाश किधर है?
Yes, sir.
आपका आवाज नहीं आ रहा है.
हाँ, यही हूँ सर.
अरे मुझे कंफ्यूजन हो गया, अविराज सिंह करके आप ज्वाइन हो गए.
हाँ, वो आज एक्चुअली दूसरे ईमेल आईडी से मैं लॉगिन कर दिया, ध्यान नहीं रहा
नो
किसी ने.
प्रॉब्लम, नो प्रॉब्लम. हाँ, आपका वो स्टैट का प्रॉब्लम सॉर्ट आउट हो गया?
हाँ, वो हो गया सर, वो लेकिन डिफरेंस रह ही गया वो. उससे कोई इशू नहीं ना सर?
नहीं नहीं, डिफरेंस थोड़ा तो आएगा. मैं दूसरी बार करूंगा ना तो भी थोड़ा सा डिफरेंस आएगा.
बाकी सब सही था ना सर?
बाकी सब सही है, सेल्फ इट मिसिंग था उसमें.
ओके सर.
ठीक है. तो हम कहाँ थे कि व्हाट इज दिस एडिशनल. सो आपको पता चल गया. मे बी आई विल ट्राई टू draw something. This is the elevation, or maybe you can call it a section. Changing some layer. So what I am doing, I am putting some additional 40 mm thickness as a floor finish, or maybe you can consider as a waterproofing on top of the slab. Okay. So yeah, same on the top of the. It will be better that I will write like this. This is suppose 40 mm. 40 mm. For wall also from internal side. So these are the floor finish, wall finish, or maybe you can consider as a waterproofing element. So these are the additional superimposed dead load on the slab. Okay, and density of that is almost considered equal to the 25. So okay, 24. So what is the weight? 24 into thickness. So we are getting additional weight on slab is 1 kilonewton per meter square. Same thing on wall also. So same values are same. So we are getting additional load on walls, and that will be applicable for wall as a 1 kilonewton per meter. Okay, live load. So we are considering live load as a 1.5. Okay, as per IS code. Why? Because this is, यहाँ पे लाइव लोड बहुत ही कम होगा, क्योंकि अगर आपने देखा तो once a while this roof slab will be subjected to the live load, so maybe during maintenance period. Otherwise कौन यहाँ पे इतना ऊपर चढ़ के जाके बैठेगा गप्पे मारने के लिए, ठीक है? So that's why, and since it's accessible, we are assuming provide some ladder, so that's why we are considering 1.5. If it is not accessible, maybe in that case we can just consider 0.75 kilonewton per meter square live load also. But okay, assume it's accessible, so we'll go with 1.5. Now, weight of the base slab and side walls. Okay, on that, what we are calculating, the water load, water depth including freeboard. कितना है? Freeboard 300 mm है, correct? 300 mm plus 5 meter water की clear height. In case of the test condition, what will be happen? So water will be filled up to the bottom of the roof tank. So this 300 mm will be also occupied by water. So that's why while calculating the water pressure on the base slab and water pressure on the side wall, I need to consider full height, that is 5.3 meter. So 5.3 into density of water is 53 kilonewton per meter square. That is a self-weight of the water and lateral load on the side wall. Okay, loading diagram. Can you see this? 5.3 meter triangular pressure on the wall and uniformly distributed pressure on the base slab, that is 53 kilonewton per meter square. Okay, all good till now? So now the seismic loads. So please pay attention, because this is most critical and most interesting and most of the time consuming uh, chapter or parameters for the seismic for the any elevated storage reservoir. Okay, so now we are going to learn seismic loads. Okay, before that, again I will go to the this section. I will ask you some questions. uh, what what are the purpose of this cross beam?
For the
To reduce the effective height.
height, sir.
Correct, absolutely correct. So to reduce the effective height of the
Column.
correct. So if we do not provide, so what happens? So the column will be
Slender
long column. Yes, slender column, it will be long column. And for that, we need to provide some huge section sizes to reduce that effective length. We have provided some cross beams. So automatically the effective length of the column is get reduced. Correct, absolutely correct. Okay. Now, again, I will ask other few questions.
Sir, how to decide number of columns here?
Number of columns, maybe you can consider based on the diameter. Okay. And like when you decide the beam thickness, so I hope you have covered your RCC part, frame structure. I'm not sure, means I don't know. So
Yes,
that
sir, covered.
okay, so maybe you have some thumb rules for that, like as IS code also provides some basic dimensions for the beam, if it is simply supported, if it is a pin, if it is a cantilever, L by 27, L by 26, based on that. So generally the parameter is like that. We may provide the center to center column is between 3 meter to 5 meter. Okay, so based on that you can go and provide the total number of the columns. Okay, and it's not like a hard and fast. So in my case I have gone with the total 9 numbers of column. Maybe you can also reduce the number of column, but in that case what happen, so your some section sizes will be increased. Okay, obviously, because the total load will be distributed amongst the all the total numbers of columns. Okay, so addition, if you increase the total number of columns, maybe your columns cross section will be get reduced, or vice versa. Okay,
Yes, sir.
so generally I go with between 3 meter to 5 meter. So, and it's like based on the diameter and geometry. Okay,
Yes, sir. Yes, sir. Thank you, sir.
now we will start with the seismic loads. So seismic design and detailing shall be in accordance to IS 81893. And for this location, we are considering zone factor Z as a 0.16, importance factor as a I is equal to 1.5, response reduction factor R is equal to 4. Okay, so now I will go with one by one. So what is this Z?
सो डिफरेंट जोन फैक्टर बने हुए हैं, उस पे डिपेंड करता है सर ये टोटल,
Correct.
मतलब फर्स्ट सेकंड एक में, फिर थर्ड फोर्थ एंड फिफ्थ, इस तरीके से डिवाइड है सर इंडिया में सिस्मिक जोन, तो उस पे जेड फैक्टर जोन फैक्टर लिया जाता है.
Correct, absolutely correct. So IS code gives one map, and a total Indian territory is divided in 4 zone. Okay, and for each zone we have specific zone factor. Okay, so for Pune, based on that map, IS code provides value for Pune is 0.16. So how I can get for that table? So yes, so I have given this reference. Refer to table number 2, पेज नंबर 16 of IS code. अगर आप जाके यहाँ पे, if you open this IS code, open this page number 16, so you will find this table. Okay, so in that, what is given that for Pune, so it is a specific location. So maybe अविनाश जी आप कहाँ पे यूपी में वगैरह होंगे, तो आपके यहाँ पे अगर आप कहीं पे आपके आसपास कहीं पे टैंक डिजाइन कर रहे होगे, तो डेफिनेटली you have to locate your location in that entire map, and based on that you have to check your Z value. Maybe your Z value will be different. Obviously at north side the Z value will be different. Okay, so for ready reference I have just add that table here. Okay, so I have not included that map, but so based on that map, for seismic zone 2, 3, 4 and 5. Okay, so it is given as a Z value. For 2, it's a low seismic intensity. Third will be the moderate. Fourth will be severe, and fifth will be very, very severe. So based on that, Z value will be get changed. So Pune comes under moderate seismic intensity. That's why it will be 0.16. And this table is directly copied from the IS table. Okay. Got it?
Yes, sir.
यस
Yes.
सर.
Okay. So now second part. Again, this will be more interaction. Our interaction session. I will ask you some more questions, and I'm expecting answer from you, so we can discuss those things. And second thing, what is this importance factor? I.
So it depends on type of building,
Correct.
of
So
which
depends.
category it is.
Yes. So what is the purpose of that building? if in case of earthquake. So what will be the allowed uh, collapse scenario for that building? Okay, so based on that we can fix whether it is a public utility building, whether it is a hospital. So this such kind of building should be remains intact or maybe very less affect due to the earthquake. So based on that we can assign the different priorities or importance factor for that. Okay, so IS code also gives some uh, guidance in terms of different tables, like table number 1 on page number 7. If I go back to this table, you can see this is the table number 1, which gives some clear idea about the importance factor I. So can you just go through this? So tank used for the storing drinking water, non-volatile material, low inflammable, etc., and intended for emergency service. This is a very important sentence. If it is constructed for to supply the emergency services such as firefighting service, so then for such tank, importance factor I will be considered as a 1.5. Clear? Except this, all other tanks with no risk to life, with negligible consequences to the environment, society and economy, that can be considered as a 1. जिससे कुछ ज्यादा फर्क नहीं होता है कि ये मेरा टैंक है वो टूट गया तो भी मेरे सोसाइटी में वाटर सिस्टम का कुछ प्रॉब्लम नहीं आने वाला है, अगर ये गिर गया तो भी there will not be any immediate impact on the human life or not any life. So maybe under that tanks can be considered as a importance factor of 1. Okay, so based on that we are considering our tank comes under as a 1.5. All good?
Yes, sir.
Now my another question. So a response reduction factor R, what is this response reduction factor?
सर एक्चुअल में सर रिस्पांस रिडक्शन फैक्टर उस चीज को डिनोट करता है कि किसी भी पर्टिकुलर लोड पे कितना पर्टिकुलर डिफ्लेक्शन शो होता है, तो हम उसको पूरा ना लेकर के एक रिस्पांस रिडक्शन फैक्टर पे यूज करते हैं, क्योंकि अर्थक्वेक कभी भी मतलब हमेशा मैक्सिमम होने के चांस बहुत कम होते हैं, इसलिए रिस्पांस रिडक्शन फैक्टर यूज किया जाता है.
Correct. So partially correct. So what we are doing most of the time, we are not building earthquake proof buildings, okay, or earthquake proof structure. Aapne most of the time maybe you can see all the advertisement from the builders. So they are mentioning earthquake resisting building. No builder can mention in their brochure like we are constructing earthquake proof. Okay, so what is the difference between earthquake proof and earthquake resisting?
Earthquake proof means is 100% protected against the earthquake, and
Correct.
resistance based upon the zones and everything, there will be resistance to the response of the earthquake forces.
Correct. So means earthquake proof means it will be very costly affair. Oh, definitely. But earthquake resisting means we are allowed to some what we can say damage to the structure, but as per the codal provision, we are giving some time to the people so they can escape from that structure, and that structure will be remains intact during the earthquake. Okay, so I'm not saying that yes there will be some cracks, there will be some minor more deflection, not limit, definitely some deflection beyond the limit, but it should not get collapsed, so it will be threat to the human life or it will be a problematic things. Okay, so that's why most of the time, or 100% time, we are designing the earthquake resisting building. Okay, but how to design that? So for that, we calculate the earthquake force, and based on that there should be some particular factor. Based on that we are reducing that intensity such a level. I'm just trying to explain in simple language. Okay, so we can finally we can get some earthquake force to design that structure, and at for that force it can be a earthquake resisting structure. Okay, so basically what we are doing, so we are reducing some response. Okay, so that's why it is called as a response reduction factor. And response reduction factor is also based on the different types of elements that we are using for the construction. Okay, so IS code is giving table number 2. Okay, if I go to the table number 2, we have to choose correct response reduction factor for our structure. So if I go, is it visible?
Yes, sir.
Okay, so for example, I will just read this first scenario. Tank is supported on masonry shaft. Is it our case?
No, sir.
Okay, tank is not supported on masonry shaft. Okay, so I will not look into this. So number 2, tank supported on RCC shaft. Okay, again there are ABC3 condition. So I will just go with first, RCC shaft with reinforced in one curtain both direction at center of the shaft thickness. Is it the case? Only circular raft will be there. So this is also our not case. Okay, same thing with second, RCC shaft will reinforcement in two curtains. Mean though we have two layers of reinforcement, still not correct. C, RCC shaft with reinforcement in two curtains in both direction. Still it is not correct explaining as per our scenario. Okay, what will be the third case? Tank supported on RCC frame. Is it our case?
Yes.
Yes, tank is supported on RCC frame. Under that, again, there are two types. One is ordinary moment resisting frame, and another is a special moment resisting frame, confirming ductility requirement of IS code. Yes, so we are using our special reinforcement, special moment resisting moment frame with ductile requirement of IS code. So that's why we have considered 4. Okay, so what are the ductile requirement? So based on that IS 13920, so it is part of the detailing. So when we are start creating some structural drawings, so we have to follow that ductiling requirement. So for earthquake, I will ask you one question. So which will be the better detailing practice, rigid or ductile?
Ductile, sir. Ductile.
Ductile, sir.
Ductile. So obviously yes, so we need to provide some flexibility so it can sustain some that earthquake force, correct? If it is rigid, what happen? So it will be brittle. If it is rigid,
It will collapse
yes, it will
without
attract
giving
more
any
force.
shining.
Yes, it will attract more force because of the rigidity. Just 1 second. Okay, so that's why we are considering R factor, response reduction factor R, as a 4. And what will be the fourth parameter? Tank supported on steel frame. So is it that case? No, obviously not, because we don't have a steel frame. So I will not read any description for that. Okay.
So what is the example of second type, sir?
Second, tank supported on RCC frame. So it can be considered as a underground or above ground circular tank, or water tank, or any structure supported on the RCC shaft, like in shear wall. Okay.
Okay.
Any problem till now?
Okay, sir.
So is it clear, response reduction factor?
Yes, yes.
Okay. So if technically, if you go to that code, and so there will be some complicated definition will be there, but on a just a very crude level, what we are doing, we are reducing some earthquake force based on our structural framing system. Okay, so that is the response reduction factor. Okay, so this is done. Okay, so now this is some preliminary data that we have just collected together as a summary. So roof slab. So what is the thickness of the roof slab? So we assume 120 mm. What is the size of the roof beams? Those are 250 by 400 mm deep. Column 250 by 250. Walls 200 mm thick. Base slab 240 thick. Gallery means the circular cantilever slab, that is 150 mm thick. Size of the floor beams is 250 by 750. The brace means the columns or beams. These beams, size of that beams are 250 by 350. Okay, and circular column, the central column, for that diameter is a 450 mm. So just we have to get just collected everything together for the weight calculation purpose. Okay, so now our first, now I will just explain some quick things. So I will draw something. Assume this is a section. Okay, so this is our tank. So this is earthquake force. Suppose earthquake force will be acting from left side to right side. So what happened? So this tank will be subjected to this force. It will resist some force, and based on that, what happened? It have some deflection, correct? So maybe because of that force, I try to draw some exaggerated scale, but just for your understanding. Okay, maybe because of that, my tank will be get deflected somewhere here. Okay, correct? Because of this, tank will be definitely deflect. And what happened? So because of this is a cantilever. Because of this, what happened? So entire earthquake force will be get attracted to this tank, correct? And it will be get transferred. Obviously, this force will be get transferred to the somewhere. Where it will go? Obviously, to the ground. So what happened if I try to draw the what is called equal and opposite equilibrium? Okay, so this is earthquake force. So definitely there will be some equilibrium force will be also there to resist this. So this amount will be same as this amount. Okay. So what is generally called? So because of this earthquake force, our main intention will be try to find out this seismic shear. Okay. And this seismic shear is typically called as a base shear. Okay. Got it?
Yes.
So during the analysis part, our ultimate aim is to find out this base shear, that is called as a V. So what is that base shear? We don't know. So we need to find out this base shear. What happens? This force will be get transferred to this container, and from the container it will get transferred to this column. Through column it will be get transferred to the ground. Okay, and it will try to resist this earthquake force. And how it will be that? And that is our intention. So that base shear, our ultimate aim is to find out the base shear. Okay. So for that, and what is the base? How can we calculate that base shear?
Cumulative.
Cumulative also, but what is the basic concept for that earthquake forces? In terms of the stiffness, correct? So if it is the stiffness is more, the base shear will be more, correct? Because earthquake is mainly function of that stiffness of the structure or the self-weight of the structure, correct? जितना स्ट्रक्चर का सेल्फ-वेट ज्यादा उतना earthquake force ज्यादा. Agree? And what happened? So entire this structure and its self-weight will be take part to contribute its value to for the calculating the earthquake force, that is a base shear. That is agree?
Yes, sir.
Okay, so basically what we need to find out? We need to find out the self-weight of the structure. Okay, so based on that it will attract the seismic force and it will get transferred to the base. Okay, so our first step to calculate base shear is calculation of the weight for different components. Okay, so it's very simple, just like a multiplication addition. So we will calculate the roof slab, weight of the roof slab. Okay, so how to calculate? So pi by 4 d square into density. So do we want to calculate this? How it is calculated? Or maybe we can just calculate one. So maybe what is the total diameter of the roof? 4.405 into 2 plus 0.4. So roof diameter is a 9.21. So pi by 4 into what is that value?
9.21
square into what is the thickness of the roof slab? So if I go to the section
120
120 mm.
120, yes, so multiply by 0.12 into 25. Okay, so I get 199.86. So roof beams. So similarly we have four numbers: density, length, depth. Here we are reducing the slab thickness because we already covered some part of the slab, so that's why we are reducing that. So for roof beams we are getting 32 kilonewton. Similarly we need to calculate the column inside, which is circular, so we calculate the weight for that column also. I will not calculate the weight because it's very simple. Maybe you can calculate at your own when you have this all the inputs. So same way we can calculate wall weight, base slab, weight of the gallery, floor beams, and the brace beams, like these staging beams, all these beams, and the circular columns, okay, below base slab, okay. Got it? Any doubt how to calculate the weight calculation? ठीक है, आगे जाएं. And of course water. So we need to consider weight of the water from the tank also, container. So in this, what we have mentioned, weight of the floor finish and plaster would be accounted where it is applicable, that's fine. Live load on the roof slab and gallery is not considered for the seismic load computation, because what we are assuming, when seismic load will be there, we are not considering any live load, correct? So अगर earthquake के दौरान यहाँ पे कोई खड़ा नहीं रहेगा ना, all will be just ran away. So that's why, even though it is just a few seconds, maybe 20, 30, or maybe maximum 1 minute, so we are not considering live load. Water load is considered as a dead load, that's fine, because it also will be some kind of the weight, and that's why I am considering as a self weight. For seismic analysis, freeboard is not included as a water depth. Okay, what is the meaning of this? The simple meaning is, during test condition, okay, what will be the test condition? I am filling the entire tank up to the bottom of the roof slab. So no, so I'm not, it's a universal assumption that during test condition आप लीकेज के लिए चेक कर रहे हो और तभी अर्थक्वेक हो गया, नो. सो ऐसा नहीं कंसिडर करते. So that's why water का weight we have just considered purely up to this only 5 meter. Okay, all good. So that's why this statement is mentioned that for seismic analysis, freeboard is not included in the depth of the water. Okay, so again, now it's a just addition of this weight of the empty container without water. So we have added all these things except water. So what is that? The weight of the empty container is 1680, and weight of the staging. Okay, weight of the staging, weight of the empty container and weight of the staging. So weight of the staging, like this one, braces and those things. Weight of the staging, braces and the columns, obviously. So that is 893.47. So IS code suggests weight of the empty container plus 1/3 weight of the staging that we need to consider for the seismic weight calculation. That's why what I did, I have calculated weight of the empty container, that is 1680.4 plus 1/3, means I have divided by weight of the staging divided by 3. So this will be my total weight of the empty container. This is given by IS code. What? Why? Because generally, again, I will try to draw one sketch here. So maybe Ajit, maybe you, those who have finished their MTech, so they already know this, but I'm just trying to give some basic things on this. Water. Okay, so earthquake. Suppose I want to apply this earthquake force assume you have the intensity, you have all the forces values. Okay, so where you will be apply this force? मान लिया आपके पास सब वैल्यूज वगैरह है, आपने सब अर्थक्वेक का फोर्स इन टर्म्स ऑफ किलो न्यूटन आपके पास है. अगर आपको ये अप्लाई करना है एंटायर सिस्टम पे,
every junction,
no, every junction, yes, it will be every junction, but ideally where it will be
at the top.
No. Any other thoughts on this? Where it will be get apply?
Bottom of slab and
Every
column
floor
junction.
height. Every floor height.
Every floor height it will be get distributed, but ideally what happen? At what location earthquake force will be get applied?
On extreme top, sir.
Bottom of slab.
No,
Top slab.
no. So okay, fine, no problem. So basically what happened? So this entire earthquake force will be attracted to the center of gravity of this system. Agree with me?
Yes, sir.
For each, आप अगर कौन सा भी force apply करो, so that force will be get not only this structure. If you applied any lateral forces, our universal assumptions is that force will be get applied to the CG of the structure. So right now I don't know where is that CG. It may be somewhere here, it may be somewhere here, or it may be somewhere here. But are you agree with me that this force needs to be get applied to the CG of this entire system? Center of gravity. Okay.
Yes, sir. Yes, sir.
Okay, so we need to apply this force to the center of gravity. But what we are assuming? So we are assuming this entire. First, what we have done, we have calculated the entire weight of this structure with different elements. Okay, empty container plus staging. So because of that, CG will be somewhere here, and as compared to that, what code suggests? So to calculation of that CG, code suggests that you may consider some 1/3 weight of staging into this container as a on higher side, safer side. Okay, so that's why we have considered a weight of empty container plus 1/3 weight of the staging. Okay, so CG will be automatically little bit shift to upside. Still I don't know where it is, but yes, we need to calculate that. Got it? Clear?
Yes.
Up to this? Okay, so up to this, what we know, what is the total weight of the empty container? After that, what is the next step? We have to find out the CG of the empty container. Okay, अभी अपना काम शुरू हो गया कि हमें we need to find out where it will be act. Okay. क्यों CG निकालते हैं हम? Why we are calculated the CG? So maybe basically what our assumption is, suppose if we converted this entire structure or entire system in a single line diagram, or so how I can represent this? So I will draw this entire framing as a single line. My mouse is not operating properly. So, and about that, I will just consider, I will replicate this entire things as a
Mass.
mass, and that is called as a, Ajit, what is called as a lumped mass. You
Lumped
definitely,
mass. Critical mass.
yes. So this is system as a lumped mass system. And now what happen? So when earthquake will be happen, it will be act on this lumped mass system, CG. It will be acting at a CG, and because of that, what will happen? The deflection, deformation, whatever it may be. So this may be sometime here, this may be sometime here. Okay, so we are converted this entire system as a lumped mass system, and this is mass M. Entire, we just calculated the weight, so we need to convert this weight into the lumped mass. हमने ये पूरा का पूरा मास एक कॉलम के ऊपर रख दिया है, जहां पे ये फोर्स आएगा it will be get deflect, and based on that, again जो आपने भी बोला था कि it will be act at the top, at the base, at every junction. Definitely yes, it will be get distributed based on that height. Clear?
Yes. Yes.
This concept lumped mass system.
Yes.
So we are just trying to simplify this. So from complex to single line diagram. So now it is very easy, correct? अभी हमको पता चल रहा है कि अभी हाँ यहाँ पे earthquake force कहाँ पे अप्लाई करना है, ठीक है, यहाँ पे अप्लाई करना है. तो at least we should know at this location we need to apply the earthquake force. How to calculate? Yes, I will tell you. Clear? Okay, now calculating the CG of empty container. So components of empty container are roof slab, floor beams. Like if I go to this, so क्या क्या इसमें components है? Roof slab, roof beam, central circular column, walls, cantilever, peripheral walkway, base slab, and roof beams. Okay, and floor beams. So therefore, distance of the CG from bottom of the floor beam. This sentence is a very, very important sentence. So from which reference we are calculating the CG? We are calculating the CG from bottom of the floor beam. Means suppose this is our floor beam. So we are calculating CG from this. Can you follow my cursor? This hand.
Yes.
Okay, so means our datum 00 will be here, correct? So if I consider this 00, from that now with reference to this, we need to calculate the CG. How to calculate? Very simple. Just start with this roof beam. Okay, roof beam name. Roof slab. Okay. 1999.887. That is a roof slab into 6.39. Can you tell me how I'm getting this 6.39? If I go to this, can you see all the dimensions here?
Yes, sir.
Is it visible? So can you please tell me what will be the CG of the roof slab from bottom of the roof beam? So we have the weight
150 plus
119.887. So ये 6.39 कैसे आया?
0.75 plus
0.75 plus
5.7
5.7
minus thickness of 120 0.12 by 2.
0.12 by
2.
2. Absolutely correct. बाकी के it is clear to all how it is calculated. अगर
No,
किसी
sir.
को प्रॉब्लम है तो बताइए. I will
Yes.
explain.
So I didn't get it, sir.
Okay. मैं डिलीट करता हूँ. So Venugopal ji, this is our 0. Okay, this is our datum.
Yes, sir.
What is the depth of the beam, roof beam? That is a
0.75.
0.75. Okay, I will open the calculator on screen also, or maybe I will write down. So from bottom of the beam, our first will be 0.75 plus we are calculating the CG of the roof slab. So from here to top of the roof, roof का CG कहाँ पे होगा? Roof का CG somewhere, not somewhere, exactly half of the thickness, correct?
Yes, sir.
So that's why what we did. So from this point to top of the roof is 5.7 meter.
Yes, sir.
5.7. अभी हम क्या है? We are came up to top of the roof slab. So means we need to come little bit down to the CG. अगर मैंने मेरे roof का ये बस only I will try to draw the roof. तो इसका CG कहाँ पे होना चाहिए?
At center.
Center. And what is the thickness of the roof slab?
0.4.
No, 120 mm.
Okay. Then that one, sir. 0.4 is, sir.
0.4 is a roof beam. If you see
Okay.
this,
Okay,
roof
sir.
beam, depth of the roof beam is a 0.4. So if you see this roof slab is 120 mm thick. So
Okay.
now we are come up to this 0.57. So that's why we need to minus half of the roof slab thickness,
Okay.
correct?
Yes, yes, sir.
That's
0.6.
why we need to 0.06.
Yes, sir.
So if you calculate this 0.75 plus 5.7 minus 0.06, 6.39.
Yes,
Okay,
sir.
so that's why we are calculated like this. 199.887, that is the weight of the roof slab, into 6.39. Okay, now what is the second? 32.265, that is for the roof beams. So Venugopal ji, can you please tell me what is the CG of the roof beam? I will just keep open this. So same way, just consider this roof beams.
Yes, sir. 0.75 plus
0.75 plus
plus the 5.7 minus
5.
0.2.
Minus 0.2. Absolutely correct.
Okay, sir.
You got
Thank
it.
you. Yes, sir.
Yes.
Thank you.
So yes. So this is the weight, 32.265 into 6.25. Okay. So same thing. What is the next column inside the tank? So weight into CG. Weight into CG. Next, is it necessary to just discuss every distance? Is it required really? How we can calculate 6.25, how we can calculate 3.225, 3.225, 0.63. It's very simple.
Yes, sir.
Can we go ahead?
Yes, sir.
So on what we did, so we calculated CG of each structure multiplied by its weight. Okay, so that we got as a 4,442 point blah blah blah, and which is divided by weight of the empty container. So divided by weight of the empty container, this one, not this one, this one, weight of the empty container. So what happened? We get 2.643 meter, and that is from where? That is from bottom of this face. So if I go, suppose this is my center of gravity, and this is earthquake force is acting. So this distance will be this. This distance will be 2.643. Got it?
Yes, sir.
Okay. So therefore, height of the CG of empty container from top of the footing means now what they have calculated from bottom. It is just calculated from the top of the footing. So that's fine. 16 plus 2.643 like this. If you see this plus 1 meter, that is why it is calculated as 16. 16 plus 2.43. Now what is the next? So there are again many things. Again, I will ask some different things. For that, I want to, not this one. Okay, so suppose this is a section. Earthquake force is acting on the tank. So what will be happen to the tank and water? So I'm asking question to you. So because of earthquake, what will be happen?
It will come in motion.
It will hammer
Water
the
will come in motion and it will strike against the wall and in translation direction.
Okay. And again, and any other answers?
it will try to give momentum to the water as well.
Yes, for the water as well. So what effect will be happen on the water?
So it will be in a rotational conditional. Water thrust will act.
Yes. So basically what happened? So because of this earthquake pressure, yes, everything will be get transferred to the water and internal. Yes. So what happened? Water will be also try to oscillate, correct? Like something like that.
Yes.
So because of that, what happened? There are two types of different mass will be created. So and which one is that? The convective mass and any idea? Convective mass and impulsive mass. Okay. So two different types of mass will be get created into this. So that's why we need to calculate those different types of mass. Okay. Convective mass. So those are basically if you see this the codal provision for the hydrodynamics. Okay. So convective mass will be So this entire pressure will be acting on the wall. So those called as a convective mass. So if I want to try to draw what is called as a free body diagram of this, so this is my wall. Okay. This is my wall. 1 minute, I'm got one phone call. Hello. Just give me a second. I'm just got one call. ओके, मी करतो तुला फोन नंतर. ठीक आहे. ओके. Sorry. Here we are. Convective mass and impulsive mass. Okay. So basically there are two different types of mass, convective and impulsive mass. So what happens? So if I try to draw some different mass system, what happen? So because of this oscillation, okay, there will be some imaginary line where at all the time water will be there, because even though if this is oscillation will be here. So if I try to draw some here and like here, at some time what happen, water will become oscillate at this wall, okay, and at this exactly after some time what happen, this wave will be generated like this. Okay, correct? ऐसे ही होगा ना, अगर ये मेरे यहाँ से आ गए तो ये वाटर की वेव ऐसी जनरेट होगी, दिस वेव, एंड मे बी आफ्टर सम टाइम ऑफ सम फ्रैक्शन ऑफ सेकंड this entire wall water will be try to impact on this side. So during that time what happen, this water pressure, this figure or the what wave of the water will be like this to acting on this
water wave.
Yes. So this above upper part, this upper portion will be considered as a convective mass, or what I am called as a MC. MC means convective mass. But at the somewhere at bottom or mid of the tank, this entire volume of the water will be constant. Okay, so this zone will be considered as an impulsive zone. So even though this oscillation will be always there, उसके नीचे कुछ तो है ना कि वो हमेशा constant रहेगा. So that will be, this zone will be considered as a convective zone, CZ, and this will be IZ. Okay, so mass of this water from convective zone considered as a convective mass, and mass of the water or liquid from impulsive zone as considered as a impulsive mass, that is denoted as MI. Okay, understand?
Yes.
Yes, sir.
So our next step is to calculate this impulsive and convective mass of the liquid. How to calculate? So code gives us some empirical formulas. So there is a no derivation like prove that, wagara wagara. So code gives a very simple empirical formulas. Based on that, you can calculate impulsive and convective mass of the structure. Okay. So these are all formulas which is directly copied from the IS code. So what it say? So can you see this first one? Mi upon m is equal to tan h bracket 0.866 d by h divided by 0.866 d by h. So in this terminologies, which is the unknown factor? Do you know m? Do you have m value? What is the m value? So we have total weight of the structure. So if we convert into the mass, from weight to mass, we got the mass of the structure. So that is known. Okay. Do you know h? Height of the tank. So that is also known. You know that value. We know the diameter of the tank. That is also known value. Again, same thing. So in this formula, only unknown thing is impulsive mass, mi. So can you calculate if you put all these values there? Very simple. So just dump all the values, you will get the mi. Okay. Got it?
Yes, sir.
So similar way,
Yes, sir.
Sir,
we
mass
have,
is
I will
of
tell you.
total.
Yeah, I will tell you. Mass. I will go to the direct calculation. So I will explain you. So this is for the impulsive mass calculation. And similarly, we have formula for convective mass calculation. What is stated that? So how to calculate impulsive mass is equal to mc upon m is equal to 0.3 tan h and bracket 3.68 h by d. Here also the unknown factor is only convective mass. Okay, so these are some different formulas. I will directly go to our calculation. So again, just see this. Design of liquid storage tank, that is okay. Total weight of the water kitna hai? We already calculated that. That's why we have converted that total weight of the water to the mass. How to convert it? Just 9.81. Okay, specific gravity. So we got mass of that water. Total water depth h, that is height. Yes, we know. Diameter we also know. Now, as per these different parameters, we are just finding out the aspect ratio. H by d is equal to 5 divided by 8.81, that is a 0.56. So just go there, check. There are two parameters are given. For h by d, if it is less than 0.75, then you need to use this formula. Okay, and if h by d is greater than 0.75, that is, then you have to use hi by h is equal to or minus 0.866, then this formula. Okay, so in our case, what is that? 0.57, that is less than 0.75. That's why we are using this first one, mi upon m tan h blah blah. So what I just added all the values. So I get ratio mi upon m is equal to 0.596. So based on that, what I did, I have the mass of the water. Correct? I have mass of the water. So multiply by that, I get impulsive mass of the water. Okay. So on the same basis, we have to calculate the convective mass. So for that, what is the formula? mc upon m is equal to 0.23 tan h in bracket 3.68 h by d divided by h by d. So based on that, what we are getting? We are getting value of convective mass. In remember, value of mass means unit of the mass is kg. Okay, so this way we are getting the convective mass and impulsive mass of the water. And I think someone has asked me about mass. I guess Bhakti.
Sir, I thought that mass is equal to total
No,
structure's mass.
because why we are taking only water? Because water is only oscillating, correct?
Yes,
That's why we are considering only, if I go
water.
back to this, only total weight of the water.
Yes.
Got your answer
Yes,
for
sir.
your question? Okay. So maybe I think we will stop today here, and by Friday we will just continue again. So hopefully we can cover most of the, we will not finish everything by next session. I think we will need another 2 more session for ESR, Friday and Monday. So by Monday, hopefully we can complete this ESR. Okay. So before closing, all good. Any question till now up to the convective mass, impulsive mass?
Yes, sir. Understood, sir.
Okay. Good. Good. Okay then. Thanks.
Yeah.
Thanks for attending. Yes.
Thank you, sir. Thank you.
Thank you. Bye.
you, sir.
Good night.
Good night.
Good night.
Thank you, sir.
Good night, sir.